All right, so did you guys come in because I said I was going to have a flamethrower? All right, give me a minute. I got to go to my car. I'm kidding. No, there's no flamethrowers, although time series databases are kind of like a flamethrower. They're hot. So I just made that up. So sorry, I haven't been drinking. I've been traveling, which is pretty close to the same thing. And I got stuck in Dallas yesterday, and nobody ever said that was cool. And so I was there for a while because there was one lightning strike near the airport. Apparently, they shut the airport down. So that was really rugged. But I am glad to be here. My name is Patrick McFadin. I am the Chief Evangelist for Apache Cassandra, which is a really cool title. But really what it means is I get to spread around all this cool stuff I know and talk to people like yourself that are, hey, what about Cassandra? What does that do? I'm a real engineer. I've got a degree from some nice university that I paid a lot of money for. And I've been using Cassandra for 4 years now. I have to keep ticking the odometer. I should just say the ingest date, like the incept date, then you guys can do your own math. It's like birth date. Never put a birth date in a database field because you're always going to have to recalculate it, right? Always just put, your actual age. You don't put that in your database. You put the birth date. I'll just give you my ingest date. So it was January 10th, 2010 is when I first started using Cassandra. So you can do your math. And it was because I had a problem. I couldn't scale my SQL databases, and I was tired of paying Oracle a lot of money to try to make it work. And I found some really cool stuff along the way. So I'm glad to be back, because I was here in January. I did a talk out at Cerner, and I told Kevin, are you in here, bud? Woo! I said, Kevin, if you put on a huge conference, I will show up. So Midwest.io, thank you very much. So I'm not going to say I'm the one to blame for that, but this is really cool. So what I really like about this is I usually talk places like Seattle and New York, and I'm go coast to coast. I'm loving that I landed in the middle of the U.S. How many of you are from Kansas City here? Awesome. Isn't it great you didn't have to get on a plane to go to like San Francisco or San Jose? Isn't that great? Yeah. I know. You probably wanted to go, right? Here, I'll come to you. There's less of me than you. So let's talk about Cassandra. That's why I'm here today. Just a quick intro. If you have never heard, how many have actually used Cassandra ever? 1, 2, you don't count. 2. Kevin, you should raise your hand a little bit. You heard about it. So Cassandra is a database. Well, I'm going to start with the basics. It's a database. It stores data, and it does it really well. It has a shared nothing architecture, which is really convenient for a lot of things. It has a masterless peer-to-peer relationship with each node. So the data is stored in a cluster, and it's meant to scale like crazy. And that's not just in speed, but in volume as well. It was based on the Dynamo paper from Amazon. The Dynamo paper is the nexus for a lot of great databases, React, Voldemort, some of the stuff that you can see in proprietary code out there has some link to Dynamo. Dynamo was a great idea. It was from Amazon. They were trying to solve a problem. The problem they were trying to solve is getting a lot of data into Amazon that had dollar signs attached to it and not going down and being global. And so it's good computer science. I talk about this, the Dynamo paper, often, because it was one of the papers that I read, and I was like, wow, this is really cool. Someone should make a database around this. And someone did, several. So what you get, or what you should get out of Cassandra based on the Dynamo and how it's supposed to work is the scaling story. You add nodes to scale, you can go up into millions of ops per second. I'm sure you could go more, but everybody seems to stop at 1 million. I don't know why. Like Amazon or Netflix did their 1 million writes per second benchmark. And then Google came out and they did, because Google Compute uses a lot of Cassandra, they went out and they were going to show those guys, they did 1 million. come on, man, do 10 or something. But what they said, well, we did it with less machines. Okay. So everyone does a million ops per second and says it's good. And a million of anything is really nice. But you see that nice straight line that's going up there? That's what you should expect because of the Dynamo paper. Without having a without having a master node or synchronous replication, you can grow your cluster and speed it up in a linear fashion. Uptime is ultra important, right? We have gotten to the point now where the world expects uptime, and this is just the fact of life. And so Cassandra is built around this idea of uptime as well. And again, that goes back to the Dynamo paper. It's built to replicate. It's hard to make it not replicate. One of my favorite questions I see on the mailing list or on IRC is, how do you get Cassandra not to replicate? It just does. You know, it's like my 6-year-old, you know. How do you get him to stop being so honest? Dad, you need to lose weight. You know, it's true. So whenever we have, you know, this replication story, we could be online all the time, and that's that always-on business, where a lot of people who use Cassandra really want to be. Multi-data center, that's just the way it works. Again, it's not just a tiny feature, it's a big deal. And so you'll see talks a lot about that. Netflix just did a really good talk about how they do active-active on Netflix using Cassandra. They push all their stuff down to the data layer and then let that just naturally replicate. There's nothing to handle at that point. So that resilience to failure, if you look over here on that right-hand side, there's a graph. We have this thing called rapid retry, and it's right now it's called eager retry in this graph, which I thought was a cool name. And it's just all the nodes work together. When they sense failure, they start routing around that problem. So this is whenever we had a node failure, and you can see the dip as everyone's figuring out real quick, and then a few seconds later, everything's backing up and going. That's with the node offline. So it responds. Hey, we deploy more Cassandra in Amazon than anywhere, and if you're expecting failure, deploy in Amazon. So, and ease of use is another problem. When I started using Cassandra, it was a little tough. You had to do a lot of work to get data in and out, and that has changed so much in the past couple of years. CQL, Cassandra Query Language, is how we do things. And wow, doesn't this look familiar? Create table, insert. We have select statements, and there's differences. And I would say if you're going to get into Cassandra, learning data modeling is very important. You know, that's probably a misconception with a lot of NoSQL databases is data modeling is gone. It's dead. We don't have to do that anymore. Wrong. I have 5 hours of talks on YouTube on data modeling. It's not dead. And those are popular. I got tens of thousands of views on those videos because it's important. I build data models for companies, and it's important. It makes the difference in whether you're going to be successful or not. But it's easy to do and very expressive with something like this. It's a typed language. And whenever you get into harder edge cases like, well, what about locking? We have that now. Paxos does optimistic locking on your row data, so you don't have to worry about race conditions and things like that. So why about time series? Somebody I heard actually said this, like pretty much all data is time series when it comes down to it. I would argue that there's some that isn't, but time series is kind of is turning into be the bigger data sets. And it's because we're collecting data at a furious pace. I know this morning in keynote there was talk about IoT. Hello, that's a lot of devices talking, right? So when we get into this problem set, like I have a Nest on my phone. I love doing this. I can change the temperature in my house from right here on stage. I did this in Poland. That was really cool. It's currently 74 degrees in my house. This is running on Cassandra. This is Nest. My little thermostat is dumping data like crazy into their database. And Google just bought them for $3 billion. Why did Google buy a thermostat? Because they had a cool car, right? Hey, this car drives itself. What else do we need? How about a cool thermostat? Yeah, that would be awesome. No! They're like, hey, these guys have figured out how to get into everybody's house. And they got a lot of data on that. Google knows when I'm away and when I'm home. Creepy. Guess who else knows that now? The NSA. So, but that's what they bought. They bought $3 billion of me being home or not being home, and then they're going to they're going to integrate the hell out of this. But it's all time series data. It's temporal data. So things like stock market graphs, oh yeah, those are obvious, right? We know that stock market graphs are time series. And with DataStax, we have OpsCenter, which is our monitoring tool. Those are typical time series graphs. Something happened at this time, and you just keep charting it over and over again. So who's using these out here? StackDriver. Here's, again, classic use. They do for Amazon. Well, it's funny, these guys are Google again. Every time I talk about a company, they get bought by Google. Anybody want me to talk about them? I'll start taking bids right now. Got any startups in here? Ooh, different crowd. That was not one hand for the record. Interesting. Okay, no startups. All right, let's talk about established companies. So AWS rack space monitoring, because it's going to go down. So that's what they do. And they use Cassandra because they needed really fast data, because it's going to be coming in at a very fast pace. So they do a couple of things. They hybridize this. They use it for quick indexes, like they roll up really fast and they put it in front of users. But then they use a batch analytics in the background to then put that data into a Cassandra column family and build out nice roll-up graphs like these right here, and it makes it fast for the end user, and it doesn't go down. And that's actually a typical Lambda-style architecture, and where they're using Cassandra to do a lot of that. And that's the storage portion of their Lambda architecture. MyDrive. One of my favorite little startups. They still haven't been bought by Google yet, but now that I talked about them, it's going to happen. So it's a cool service. They actually watch all your hard drives in your data center and tell you which one's going to die. And when I ran infrastructure, I would have paid for this, because I always lost like 10% of my disks, and it was like, throw the dice. Well, that's what they do. Is they watch smart data, and they watch, they find out what's going on. They're running on Mongo. Now, Mongo was an easy choice because they're just dumping JSON in there, and they figure, well, it'll scale later, and it didn't. And so what they have is this massive queue processing problem. This blue line is their queue depth of how waiting process stuff, and it's just kind of building up over time and never really catching up very well. And they said, we're over. This is in a blog post, by the way, if you want to go check it out. And they just decided, well, we're going to switch to a database that's built for time series in a lot better way, and that was Cassandra. And boom, you could see the little graphs where they changed everything out. The flat line after that, which I didn't put anything about, that's when they found out that their queuing mechanism had a bottleneck. So Cassandra eliminated the ingestion portion of the bottleneck, and then they found a new bottleneck. And that's kind of the fun of fixing problems, is you find new ones. Paddy Power. How many of you have heard of Paddy Power? Not in the US. Now, first time I went there, this is in Dublin, Ireland, I thought Paddy Power must be like a energy company or green power or something like that, right? No. This is a gambling website. They're bookmakers. When you want to bet on a Ulster game, because I know you do, you go to Paddy Power. But they're much bigger than that. They're legit. You can if you're in Europe, you can bet on US football, European football, say football, and any sport you can think of. And so this is a pretty big deal, right? Whenever you make a bet with your bookie, I don't know if you have one, but I do, and you don't pay him, what happens? You break your legs, right? So this is kind of serious. And it's like a bank, in a way. You do not lose transactions, because people care about the fact that somebody won or lost and get some money out of it. So they have uptime guarantees they need to maintain. They can't lose data. They had a problem. One of their data centers went down. Their one data center went down. Guess what? Paddy Power's offline. So they embarked on a fix. And I actually got to go there. That was me, next to this green thing. I don't know. Anyway, so this green thing on a little car. And that tells me everything I need to know about them. We had a really good talk, and now they're using Cassandra. John Turner, I just saw him a few months ago. Happy little Irishman. He's very happy because he's got a database that's going to scale the way he wants it to. It just doesn't cause problems. The thing I love to talk about Cassandra, it should be the most boring thing in your data center. I've got so many people that are like, dude, I need a new job. Why? Well, we got Cassandra in here, and there's nothing to do. Sweet. There's a guy who works on my team, Al Toby. He used to work at Uyala. Bored because he had a Cassandra cluster that was running for 3 years. They moved to 3 different data centers and never had any downtime. They kept moving the data around. Never had any downtime. That is so boring for someone who wants excitement in their life. So now he works for me, and I keep him plenty excited with cool things to do. And the Internet of Things. You know, here's our Nest thermostat, the really cool one, the $3 billion thermostat. That's going to be the problem, right? So here we are. We got everything talking IP. It's going to be something. So why Cassandra for time series? So I think I've convinced you that there's a problem out there, that there are people doing some things. So let's talk about the technical details, as this is a technical talk. So we know it scales. Got that. Check the box. Resilient. Doesn't go down. That's great. Good data model. I'll explain more, but hopefully you understand that that's possible. And it has an efficient storage model. Now, that's not on your list, I bet. But this is the secret sauce, and this is what I'm going to explain to you and maybe convince you this is a good choice. So what about that? So I just asked this. So I don't know if you guys do much MySQL performance tuning. If you have, you know this guy, Baron Schwartz. He and I have been exchanging emails lately, really lately. I'm going to get on a plane tonight. I'm going to go talk to him tomorrow. He had this great blog post right here, time series database requirements. Man, he laid down the law because he's Baron Schwartz, right? He's the man. And he's like, you know what? I'm thinking of a database. And he just really railed it out. So this is what he said. And I know it's like a wall of text, and I really don't expect you to read this. But he listed off, this should have all this stuff. And I'm like, at first, there were several. I was like, Baron, you're talking about Cassandra. No. And finally, he's like, all right. So this is distributed by design. I'll explain how that is the truth. Send the query to the data. I totally agree. If you have a 1,000-node cluster, you do not want to do scatter gather. Efficient per node. I can prove that too. And fast and consistent. 1 million writes per second seems pretty fast. So he talked about this, and this is where people's heads are now. We're trying to solve this problem. There's some really great proprietary time series databases that are super expensive because this is a hard problem. Well, I happen to have one that's for free. So let's talk about an example here. So I have the weather station example. Everyone seems to be getting bored of this one. I'll have to change it up to something else like stock tick. Oh, wait. Never mind. I'll do that one too. It's hard to do a good example on time series because it's all kind of boring, but hopefully this works. So we have a weather station that's collect data, and then what do you do when you collect that data? You dump it into a nice graph. Awesome. And you can fit this in your head. So let's do some data modeling. So when you do Cassandra data modeling, you start with your use case first. You build your queries, and then you build your data. It's exactly opposite of relational data modeling where you have your data, you build a model, and then you go take that big, you saw that poster board thing of the ERD on the wall, and everyone kind of walks up to it and says, oh, now I need to write my code. Here's my path. I'll do 16 joins and a left outer join. No, completely reverse with Cassandra. It's an application database. It is built for applications. You do things with your application, you make the queries that need to be happening, you write your data model to that. So the queries I need to support, I need to store data per weather station, and I need to store time series in order from first to last. So let's see what that looks like. So here's my create table. I have a temperature table. It's real simple. I have a weather station, the time that it happened, and then temperature. And the primary key in this case is going to be a weather station ID and an event time. That's the unique part of the data. So a weather station with a event time. So I have my inserts here, very simple. I have one weather station that's 1, 2, 3, 4, A, B, C, D. I don't think it's real. I don't know, though. And I have some timestamps. Each one of those is, I'm collecting data about every minute, and each one has a temperature. Very simple, right? Well, when I do a select off of that data and I say, give me weather station ID 1, 2, 3, 4, A, B, C, D, I get a nice table in CQL. This is what I want, rows and columns. The rows are all going to have the same weather station ID, but the event times, it's going to be ordered by event time, top down, and I'm going to get different temperatures. Now, why that doesn't look abnormal at all. This is what we expect is in SQL, right? I get a table of data. Great for programmers, right? But what's actually happening underneath? Animation. So what happens is this is how it's stored on the disk. And this is what makes a huge difference. And this is what I explained to Baron, was that the data is sequential on disk, which makes it a much more efficient model. So what starts out with just that weather station ID is going to have each single data point across. And it's going to be in order, in sequential order, on the disk. And when I add more data to that, it's going to append to the end of that list on disk. Now, why is that a good idea? Let's face it. When you're working with the server, your biggest problem is the disk. It is the slowest piece of the puzzle. CPUs are super fast. Memory, no problem. You get to the disk, you go from nanoseconds in memory to milliseconds on disk. So making that efficient is really the name of the game. So how are we going to actually do that? Or how does that work in a query situation? So let's go back to our query. This is a typical type of query. I have an event time that I'm looking from and to. So I have my select my weather station ID, but then I'm going to grab it for a certain range of time. That's what you would expect on a graph, right? And we call that a slice operation. What that does on the disk in the storage model is it does a single seek on the disk. The seek time is what's going to kill you. This is really the big deal. Seek times are, with SATA disks, remember, SATA is only one letter away from being Satan. SATA disks, you're looking at 15, 20 milliseconds of average seek time. And, and then if you really want to get lied to, you go read the manufacturer's specs, and it's only 5 milliseconds. But still, 5 milliseconds? You do 10 of those, it's going to hurt. So we do a single seek on disk, and then we read it across in a single slice, and it goes up into the CQL table as a representation. So that single seek on disk with a single pass keeps that average seek time manageable, but also keeps it so that whenever you get the data off the disk, it's efficiently streamed back to you, the end user. This is a slice operation. This is what makes time series really hum on Cassandra. Now, let's get into a little more detail-y here. So if you're a programmer, I hope you like this model better. Because if I was thinking about it in a sequential form in a program, it's harder. But if it's in rows and columns, awesome. I can just create an iterator, row next, row next, row next, get all my data. So we get some additional help as well. So seeks are, whoa, got psychedelic on me. Sorry. I'm going to go back. Yeah, so AV guys, thanks for turning on the 1968 filter there. That's awesome. So man, it's like your disk is you, and you are your disk. You dig? Right on? All right. Yeah, I can see you. Hey, help this guy, man. He's tripping hard. All right. So that was enough fun. So we're going to try to seek as least amount of times as possible, and that is the name of the game. Again, our disks are not in our helping us. They're not on our side. So whenever we have this situation of, hey, I'm going to go grab a lot of data, we want to try to keep it down to just one seek. Well, we have a few things that will help us get there. When the client reads data, there's a Bloom filter in place, because everybody loves a good Bloom filter, and that's going to minimize the amount of tables that it has to read. The data files on disk, there's going to be a lot of them. So you want to try to get down to the least amount as possible. And those data files are going to be, they could be thousands of them. Bloom filters, of course. I feel like in 2014, I don't need to explain Bloom filters too much, but if you need to go find out more, they're on Wikipedia. But that's just going to give you a smaller list, right? It eliminates a lot of the cruft. Then we have our key cache that gets involved. And if the key cache has a hit, it goes right into that data file. You get your data, you're in and you're out, and you're done. Now, we also have a partition index that gets you closer. But all of these things working, in the least optimized setting is still going to give you a few seeks. And that's what we try to minimize. So your total seek time is your disk latency times the number of seeks. Plain math. No calculus, right? So we're going to try to help that along. So what we know is that use that first part of that primary key to get that data location. And I'm going to explain how that works in a minute. But Baron's thing is like, hey, I'd like to go where the data is. Got that. We minimize the SS table seeks with Bloom filters, key caches. And we find the data fast on disk, on the SS, or we find the data fast in the SS table, which is where indexes come in. So how about those indexes? Well, we have a new feature as of 2.0 that actually helps out quite a bit, and that is a MinMaxValueHint. And what it is that we actually look inside the SS table, and we do range indexes on something that was defined in the primary key. So like a date, that's a range index. It has order. And so whenever I ask for something like, I want to select from this time to this time, like from, on April 3rd, then how am I going to get some help here? If I look at what the min and max events on each SS table, it's clear that it's in one of those, but not in the others. So that index is going to help me. So as it reads the indexes for each SS table, that could be a potential, I might have to do 3 seeks if these indexes didn't exist. But since that middle one there is right in the range where I want to be, I go directly to it. I say, which one is it? It says, this one. 1 seek. And even if you're using SATA, you're still a little happier. You won't be happy with SATA, but it does minimize the amount of time it takes you to get to the disk. And when you're doing 1 million of these a second, that could really count. So how about that 1 million a second? So, man, this is just getting weirder and weirder. I actually like the Kafka logo now. That's a good one. And I just realized I didn't update my slides. I made up my own Storm logo, but that just got voted in, I saw. That's cool. Because if you have a great open source project, you got to have a logo, right? For Cassandra, we have the Eye of Nightmare Fuel. That's a good one. But here's some options. So if you're going to put data at an enormous rate into a database, you got to have a plan to move data at an enormous rate. You can't just throw that into some Ruby code and be happy. Trust me. You're going to have a plan. And so what I work with a lot of people that ingest large amounts of data, and there's always some more to it. And here's I'm going to walk through a few of these. I mentioned Kafka. Apache Flume, still pretty valid out there. I think a lot of people just saw it for log files, but I use it. Storm, I should say Apache Storm. And Spark Streaming is the new cool kid in the block. And then some custom applications. Your custom code, I'm sure it's written in Go, because that's cool. And but now Rust is cooler than Go. San Francisco, show up. Rust is cooler than Go, but then Go is cooler because it's bigger and badder. I don't know. It depends on how soon it is to Google I/O. So Kafka and Storm. We have a good combo here. We have a queuing model that works really well that scales and a processing model that scales in the same way. If you're going to have a linear scaling database, you better have horizontal scaling in all your tiers or you're going to have a bottleneck, right? So that's what this actually brings pretty well. And I mentioned the Lambda architecture. Storm, of course, was where that really got into everybody's vernacular. Oh, Lambda, Lambda, Lambda. And because of Storm, and then we have some batch processing on the background. Well, this is used in a lot of places. And Kafka is a really great queuing system for that once and only once, guaranteed order, that kind of thing. So I see this quite a bit out there. Typically, it would be like something like rollups, processing rollups in the stream. If you are doing real-time data, you had better have a real-time database. And you better have a real-time rollup strategy. If you're doing things in batch on Hadoop, I'll see you tomorrow. Sometimes you don't need that. When I work with real-time data, it needs to be human real-time, as in I'm looking at a plasma screen. I need to know something happened right now. Well, if you're running that in MapReduce, you're going to get a report tomorrow in your inbox. That's not what people are looking for in these cases. Flume, I built this one a couple of times. I had a F5 load balancer. Those are great boxes, by the way. Totally hackable. I had F5 load balancers, 3 data centers, and they were just spewing every web event that would come into my F5. I had an I rule that would pick it out, create a marker, and then when a server response back from the load balancing pool would come back, I would mark when the response time was and how long it took, and send that. I would just drop it into a syslog packet and drop it into Flume. So there was thousands of these per second, right, just pouring in, and it had tons of information about my web serving infrastructure. And again, that was something I needed to know. At the time, I was working in a company called Hobsons, which did a lot of online applications, like college applications. If you went to college in the past 10 years, you probably went through my systems a few times. And that's one of those things you want to know now. Because trust me, if someone's filling out a college application, you're affecting their lives. They tell me. And you don't want to have this like it's a batch. You need to know now that, oh, we're getting a bunch of 500 errors on our app servers. We better go fix that because we're affecting people's lives. So it's important to have that real-time thing. Now, what I did with this Flume channel, with this Flume processing, is I took every web event and created 9 different inserts on that. That was pretty fast, too. So, or 9D, 9-0. So it was putting, for every 1,000 requests, it was doing like 90,000 inserts into Cassandra. That's a lot of data. But I was rolling it up in every which way you could think of. Now we're doing Spark. I was at the Spark Summit last week. You never saw so many Hadoop refugees ever. It was great. Everyone's in there, please make it better. So no one was unhappy, though, because it was a love fest. And so Spark is a first-class citizen on top of Cassandra right now. And it's doing pretty well. People are excited about it. That means whenever you ingest data in Cassandra at the speed you ingest it, Spark will run on top of a Cassandra data set. It will run on top of a table. And you can analyze it in place and put it right back in the same table. It is really fast. It's probably about 30 times faster than running it on HDFS, and probably even faster as we keep optimizing this. And it's all in open source, which is something I fought hard for. But if you want commercial, Databricks and DataStax are working together. We are partners and making this a commercial entity as well. So Spark, Cassandra, this is that final leg. Well, we have Spark streaming, but we also have the batch analytics for the Lambda architecture to fit it all together and make it happy, just running on Cassandra and be happy. That means no more Zookeeper. Oh, yeah, I got like a couple. Yeah, anyway. I just don't like Zookeeper anymore. All right, so when you're dealing with this at speed, when you have 1 million writes per second, you have to do 1 insert every microsecond. So how are you going to do that? How are you going to deal with the collisions? So the primary key in your data corresponds to placement. So whenever I write that primary key, it's going to go drop into there, and you're going to be done with your data. So here's our weather station ID. That's how it gets in there. So how does it replicate? I'm going to walk through this really quickly. This is more of just kind of an intro, but if you want to know more data about it, I have a whole intro talk out there. So if I have somebody named Jim out there, these are all my primary keys right here. So this is my data table. Each key gets hashed by an MD5, okay, and that's cool. So we have a consistent hashing algorithm creating a hash of each primary key. So when we look at a token ring, this says node A, B, C, and D, by the way. Trust me. We're going to assign a range of values in that 128-bit number space. So a quarter of that number space in each node. And each node is going to store the data that's hashed in that range. So for instance, Jim, he hashes to this 5E0 value. Where does that fit? It just happens to fit inside the range that's on node C. And as I walk through my data set, you can see how that hash value then distributes the data in a kind of a random fashion and in a distributed fashion. Now, if I was to double the number of nodes, each range would get smaller. So that's where your linear story comes from. It's literally, you're having the load on each one if you double your ring. So that's how we distribute data. Now, the replication is somewhat simple in this case now, because what we do is we assign a primary range of data to a single node, and then we make every replica, in this case we have 3 replicas, also responsible for that data as well. So when the client writes the data, it's written asynchronously to every single node at the same time. There's no master node involved. And that means you don't have as big of potential for failure. There's a whole issue of consistency, like how do you know the data got to those 3 nodes? different talk, but that's what you need to look at as a consistency level. So we also have one other thing. It's called a TimeUID. And a TimeUID is a data type. So you take a timestamp to the microsecond, and you add a UID component to it. Just basically make a random, unique identifier. Now, these are really important, especially if you're ingesting data at a high speed. More than likely, with the timestamp, you're getting a millisecond or even a second resolution. The potential for collisions is really high. So if you're in a condition where this might be the case, this is a good way to make sure you can take in the same timestamps and not collide data on the same, potentially on the same partition of data. So what do you get with that? Well, you get it's a standard of sorts. That's a great thing about standards. So many to pick from. It's a version 1 UUID. So it is sortable, meaning that UUID that you get out of there that looks like that actually does have sort order. It's temporal. You can sort it from last to first. And then finally, you can reverse it. So this equals this crazy date right here. So you can actually pull out data from it, which is handy. So let's do our final example. I have 5 minutes, and I bet you we can do it. Or do I still have 5 minutes from lunch, or did that? I don't even know anymore. These guys are just like, go. So here's our new thing. We're going to actually do some stock tickers, but we know that stock ticks come fast, and they come really fast, and they have really crappy timestamps. So we want to get all the trades for a symbol and a day, get a trade for a single date and time, and get the last trades for a symbol and date. So our data model is store that data per symbol and date, so what trade it was, and we're going to sort it in reverse order this time. There's a trick to this. And then make sure that every transaction is unique. We can't lose it because that's money, right? Give me another slide. There we go. So here's our data model. Kind of similar to what we did with the weather station. A little different, though. The primary key here has a symbol and date combined. That is the unique row key. That's going to give that data locality. Also, I have this clustering order by. In my data model, I can create ordering of the data itself. And so in this case, I have my trade, which I'm going to reverse order. So that means as I'm entering data in here, and these UUIDs actually are a timestamp, they're a time UUID. When I enter those in, I'm actually going to store it in reverse order. So that the last thing that happened is at the top of my list, and the first thing that happened is at the bottom. So when I ask for Netflix, and then I have my epoch date, which is 340, that's how I'm partitioning my data. So I get that reverse order. So whenever I ask interesting questions of that data, and I have a really good example of how, what I'm actually doing is I'm storing it on disk in that reverse order now. That's a huge efficiency step, because if I know my data model, I'm going to have that in reverse order. Great. So what does that mean to you, the programmer? So whenever I ask really interesting questions, this is very typical of this type of data model. Give me the last 3 things that happened. I don't know what they were. Give me the last 3 things. So I have my select where I say limit 3. Well, instead of going all the way to the end of the disk and falling off and going where Johnny Depp lives, I'm going to go from the beginning of that list and just go 3 in. 1, 2, 3. And then return it back to the application. It's very efficient on disk. It doesn't have to scan all the way to the end of the disk and then find the order and then reverse it and send it back to the user. That is really inefficient, and that will take a long time to manage. So whenever I know my last 3 things are, this data model is where fraud detection lives. This is where things like product recommendation lives. Early warning on a lot of things live here. So this is a great data model for that. So I got more examples out there. Planet Cassandra, great resource. 300 plus 5-minute interviews. Tons of companies that they love to brag about what they do. If you have a use case, you can probably find somebody that's doing something similar out there, and they talk about what they do. I have a bunch of videos out there, tons of stuff. And as of yesterday, DataStax has free training, revamped our training site, academy.datastax.com. Check it out. Free Cassandra training for the masses, even you. And got to plug my summit. I'll be talking at this a lot. So this Cassandra Summit is the 10th and the 11th. We have a training day, and then the free admission, well, it's sold out. I think that's kind of funny. We're only accepting training day people now, so I believe I think that's the only one left. But if you're interested in knowing about this Cassandra Summit, is going to be a blockbuster. We got people lined up like crazy, like Target and Sony. Apple has some talks. So if you want to see what the big kids are doing with Cassandra, good place to go. And that's me. Follow me on Twitter, at Patrick McFadin. That's 1 D, 1 I, 1 N. And you get lots of good information about Cassandra. I don't talk about much else, and that's it. So do I have time for questions? None. I'll be in the back. All right. Thank you very much.